Good day, everybody, and we meet yet again. And today we just want to cover Newton's laws of universal gravitation. Okay, so obviously we have already covered Newton's laws of motion, and this is the law that has to do with the attraction between two bodies, right? So if you haven't subscribed, please make sure that you hit that subscribe button. And obviously, if you like this lesson, just hit that thumbs up just to give us some encouragement. Okay, so let's get right into it. Okay, so first of all, when we talk about Newton's law of gravitation, okay, so we are talking about the law of attraction between bodies. It's a non-contact force. Okay, it's a force that involves two bodies in the universe. And how it's defined, it simply says two bodies in the universe, okay, will attract each other first of all with a force that is directly proportional to the product of their masses, okay? Or you can simply just say the force will be directly proportional to the magnitude of their masses, right? And inversely proportional to the square of their distance apart from their center of mass. Now, please, that's very important. So we say it's inversely proportional to the distance, right, apart from their centers of mass. So in this case, to the square of the distance, rather, apart from the centers of mass. So that becomes very critical when we now have to calculate, because it means that to calculate this force, you always need to determine the distance from the center of mass to the center of mass. What I simply mean by that is that if you've got two bodies, right, the one is M1 and the other one is M2, right? Okay, so how we will calculate the force between M1 and M2, all right, you will consider, now please note, we know the magnitude of their mass, okay, but when we take the distance, we don't take the distance apart from each other, all right, between surface to surface, but we rather take the distance from center of mass to center of mass. So in this case, this should be the distance r that we are referring to. Okay, right, now not wanting to go into many gory details, right? So when we put this equation together, we now get or obtain this equation. Now we are moving from proportional sign to an equal sign, and every time that we do that, we must have a constant so that we know by how much it is equal to the other, right? So in this case, it's equals to g, right? We call this the universal gravitational constant, and I'm going to give you the value in just a little while. So that's m1 m2 divided by r squared. And remember, we said this distance here is the distance between center to center, okay, center of mass to center of mass. Okay, so in this case, we are usually given g. Okay, so if you are, whatever exam that you may be writing, remember that you are always given that value of g. Okay, and in this case, we simply say the value of g is, okay, 6.67. This is times 10 to the minus 11. Okay, and this is measured in Newton meter squared per kilogram squared. Okay, so I'm going to try and squeeze it there. Okay, so that's Newton meter squared per kilogram squared. Now, not that you really need to remember those units, okay, because the main thing is that we're simply going to substitute for that constant, right? So now, what it simply means is that whenever we want to calculate the force of attraction, remember we said this universal gravitational constant has to do with the force of attraction, okay, between two bodies. Now, if you remember, this law does look somewhat similar to another law, isn't it? If you think about Coulomb's law, okay, right, Coulomb's law, instead you've got the Coulomb's constant there, K, that's Q1, Q2 divided by r squared, isn't it? Okay, so in a way they look somewhat similar, and the only difference is that with Coulomb's law, remember that you've got unlike charges and like charges, that unlike charges attract and like charges repel, right? But here we are simply dealing with mass, which does not have any polarity. There's no positive or negative mass. And in this case, that is why we always say it will be a force of attraction. Okay? So now I want you to think about the significance of this, right? So what this simply means is that if you're looking at, and this is how we calculate the weight, okay, say this is the Earth. Now remember that the Earth, okay, this is the center of the Earth. Remember that the Earth has got a particular radius, okay? And in this case, I'm going to give you the radius of the Earth in just a little while, and also has a mass. Now, suppose we've got a person or, whatever object is on the surface of the Earth. If we didn't consider this issue of the center of gravity, we would make the error of saying the distance between the Earth and the person is 0, right? If they are standing there. But remember, when we talk about the from center to center, that is why we're going to say, well, it's from the center to the center of the person, and so this will be the radius of the Earth. Now, I just want to quickly show you from a at least for those of you in South Africa who are writing either the NSC or the IEB exam, that you are given, by the way, the mass of the Earth as well as the radius of the Earth. So you won't necessarily need to remember them off by heart. Okay, so let me just pull a question paper just to show you the formula sheet that you are given that. Okay, so there it is there. Okay, so if you think there's your table of constants there, and that's the radius of the Earth, RE, that's 6.38 times 10 to the power 6, as well as the mass of the Earth, which is ME 5.98 times 10 power 24 kilograms. So as I said to you, you'll never need to necessarily remember those values, right? Now, what is quite important to remember, right, is that whenever they ask us questions, which we're going to look at, okay, I wanted to make this lesson quite short and straight to the point. Okay, so when we consider the calculating the weight or the force of gravity, now what you're going to do, if we wanted to find out what is the force of gravity of this person on the surface of the Earth or near the surface of the Earth, so what you simply do, you use that formula and you say, well, the force of gravity, right, that's G, that would be the mass of the Earth, right, and it would be the mass of the person, okay, so divided by, now what would be R here? It would be RE, which means that it's the radius, okay, obviously, I mean, the distance between the surface of the Earth and the center of the person is quite negligible, right? So in this case, you would consider that to be just the radius of the Earth. Now, having said that, I also want to make you just aware of something. Now, imagine we've always calculated force of gravity, or what we call the weight. If you remember, we always use weight is equals to mass. Okay, so suppose we've got an object with mass m. So weight is equals to m multiplied by the gravitational acceleration. Okay, right, so I want you to think about that. So we know that the weight is the force with which the Earth pulls an object. So let's take this person once again. Okay, right, so I want to show you where this value of G is equal to 9.8 comes from, right? So how we get the gravitational acceleration, we say, well, the weight is equals to the mass of the person, okay? Let me just call it MP, if you don't mind, right? So the mass of the person, or it could be any other object for that matter. So if I want to get the weight of the person, remember weight is a force, okay? mass is well, basically the measure of the inertia of an object, right? So what we simply say is that if I wanted to find out what the weight is, I'll say the mass of the person or of the object multiplied by gravitational acceleration. Now I want you to please see something. But we also know that the same weight, okay, of body P is actually the same as the force of gravity of that body, right? Weight and force of gravity, it's exactly the same thing, isn't it? Okay, so now I can say, well, if this is the same, then it means that mg, right? So the mass of the person multiplied by gravitational acceleration, which is the weight, is also equal to g. Now remember, so we said that the weight would be the mass, or it's the force of attraction between the Earth and the particular body, right? So it would be mass of the Earth multiplied by the mass of body P divided by, now what would be the distance? We simply consider the radius of the Earth, and please remember that that distance is squared. Now, notice what's going to happen there, all right? To show you that gravitational acceleration is actually independent of the mass of an object. Can you see that I can divide both sides by mp? So if I decide to divide by mp on both sides, this will cancel that, and it will cancel that. So now what am I left with? Gravitational acceleration of any object, okay, now depends on the following: the gravitational universal gravitational constant. In this case, because I'm talking about the Earth, right, it would be the mass of the Earth, and I will divide that by the radius of the Earth squared, the square of that radius of the Earth. So this shows you that gravitational acceleration is actually independent. Remember, every object experiences, well, here on Earth, that is, right? Every object experiences a gravitational acceleration of 9.8 meters per second squared, right? That's what the average actually is, right? So in this case, whenever the examiner asks us to prove that gravitational acceleration, please note there's a difference between gravitational force, which is this guy here, right? Which is that guy over there. Remember that weight and gravitational force, that's exactly the same thing, right? So there's a difference between gravitational force and gravitational acceleration. When we talk acceleration, we're talking about this guy here, okay? And it's equals to gme over re squared. Now, just to quickly show you, once again, you'll see that if you consider your your data sheet, your formula sheet in the exam, you'll see there's that distance, formula given there, okay, for gravitational force, and there is the formula that you use for gravitational acceleration, okay? And you can see that it does not, this would be the mass of the Earth, this would be the radius of the Earth, and therefore it is independent of the mass of an object. So what I want to do quickly, ladies and gents, is just show you the application. This is quite a straightforward application. Okay, so I want to show you quickly how would then apply this principle. Let's take a question. Right, so let's take this question. They said determine the gravitational pull between the Earth and a man with a mass of 70 kilograms if, all right, so then first question, he's on the surface of the Earth, that is at sea level. So very straightforward question. We've got the mass of the person in kilograms, right? And by the way, something that I almost forgot to mention, that the distance must always be in meters, right? So we're simply going to apply, we want the gravitational pull, meaning that we want the force between the Earth and the person, right, if it's on the surface of the Earth. Now, let me draw that first. So you are looking at now, here's a person standing on the surface of the Earth, right? So in this particular case, I know that the distance would be just merely the radius of the earth, right? Okay, so that would be RE. I tried to squeeze that in there. Okay, right. So the radius would be the radius of the earth. And so what I want to find out is the force with which the earth pulls the person, right? So I'm going to say, well, force is equals to G. That's M1, M2 divided by R squared, or you can use D squared if you want to. Okay, but I realize it's going to be RE squared. Okay, so that's the mass of the earth, mass of the person, right? Okay, now all we need to do, ladies and gents, is just substitute all our values, right? The value of G, that's 6.67 times 10 minus 11, okay, multiplied by, well, the mass of the earth. Remember, we said that we are given that mass. That's going to be 5.98. So in this case, that's going to be 5.98, okay, times 10 to the power 24. Okay, quite a large value that. Right, now you don't need to put in the SI units as you calculate. Okay, please just remember that, otherwise it will just make your you're working out quite complex when you've got all those SI units there. So multiply that by the mass of the person. Remember, they said to us it's 70 kilograms. Okay, I'm just going to show you something in just a few just now. Okay, divided by, all right, so in this case, using this principle, what would be the radius of the earth? So the radius of the earth, in this case 6.38 multiplied by 10 to the power 6. So that's going to be 6.38, okay, multiplied by 10 to the power 6. But remember, this should be squared. Okay, sorry for that ugliness over there. Okay, so 6.38 times 10 to the power 6, right? And all that we need to do now is just punch this in our calculator, and I'm sure you're going to do that quite swiftly. All right, okay, in fact, you know what, let me just show you how I would actually use the calculator. I'm not trying to promote any calculator here. This is the calculator that I use, but I just wanted to show you how I would calculate something like that, because I just want you to be more efficient when it comes to, making calculations. Now, you'll see that I've got my fraction button there. So I would say 6.67. Now, please note, I'm going to use that exponent button at the bottom there next to your answer button, right? Obviously, if you're using a different brand, it doesn't really matter. So I press that button, and I want minus 11. So I'm going to use this minus over here, not the one there, right? So that's minus 11, and I multiply that by 5.98, okay? Again, exponent button, and power 24, multiplied by. So I'm trying to show you that you don't necessarily need to keep using that exponent x to the power of button. This actually saves you a lot of time. And then let's go to the bottom. I'm going to open the bracket there. So that's 6.38, okay, exponent once again, and all I need to press is 6, and I will square that. Okay, right, and I'm sure there's the answer that I got. Okay, 685 rather, 0.94. Okay, so I'm just going to round it off. So this is going to be 685.94. And please remember, because we're dealing with a force here, remember that is measured in newtons. Okay, so that would be that force there. By the way, remember that I said to you that the force of gravity, okay, remember we're looking for gravitational force. This would be the same force as the weight. You remember that? Okay, so I'm trying to show you that actually, if we use this, let's check if we would get the same answer. So this would be mass multiplied by gravitational acceleration, isn't it? Okay, so you would say this would be mass, which is 70 kilograms multiplied by 9.8, and I'm going to do that with you, okay, so that you can verify it. So that's 70 multiplied by 9.8, which is, okay, see that, 686, which is more or less the same answer that we got there. Okay, so that's 686. So in this case, of course, if the examiner was very it's very specific for you to answer it using Newton's gravitational law, of course this would be the way to do it. Okay, right, now let's go to the second question. All right, now they say this person is now, okay, so we want the gravitational pull between the earth and the man with a mass of 70 kilograms. If now he is on an aeroplane which is 10,000 meters above the surface of the earth. Now, very important for you to note, ladies and gents, in this particular case, because the person is no longer on the surface of the earth or even near it, so you cannot use this particular formula, because this will only work for objects that are on the surface of the earth or near the surface of the earth. Okay, but the moment that we now are a significant distance away from the surface of the earth, then you no longer can use this one. You are now compelled to use Newton's law of gravitation. Okay, so what I'm going to draw there, all right, my drawing skills need some prayers. I just know science and not drawing. So if that's our airplane, okay, whoa. All right, so now we know in this case it's no longer on the earth, but it is 10,000 meters. Now note, it is 10,000 meters from where? From the surface of the earth, right? So now when we calculate this gravitational force, I'm simply going to say, okay, now for the second question, it's going to be the same formula. Yes, so that's G, the mass of the, oh sorry, we're still looking for the mass of the gravitational force of the person, not the plane. Okay, so it's going to be the mass of the earth multiplied by the mass of the person, right? The 70 kilogram mass. Sorry for drawing the aeroplane there as though we are calculating the mass of it, or rather we are calculating the force of it, right? So divided by, now I'm going to use d squared. Okay, right, and by the way, nothing wrong if you had used something else. Okay, so I'm going to calculate that force. We said it's going to be 6.67. I think I'm going to run out of space there. Times 10 minus 11. We said the mass of the earth again. That's 5.98 times 10 power 24. Okay. And we said the mass of the person is 70 kilograms. Now, the part I wanted to get to is the part where we are dealing with the distance. I know many people would fall into the trap of saying, oh no, but I know the distance is 10,000 meters. Be very careful about that, because remember, when we are calculating the force, we always take between the two objects from their center, okay, to the other center of mass. Can you see that? So it means, remember, they gave us 10,000 as the distance from the surface to the center. So this here, if you want to call it, in fact, so this would be the radius, okay, of the earth from there till there, and let me call this small r, okay, that distance between the surface and the center of the person. Okay, so note in this case, it means that d, the distance, the total distance, okay, so I call that d over there. So the total distance will be the the radius of the earth plus that distance that we are given there above the surface of the earth. So in this case, it means I will say 6.38 times 10 to the power 6, and I am simply going to add 10,000, and please note that's in meters. Both of them are in meters, and please don't forget, ladies and gents, you simply need to square that distance. Okay, I know you'll work it out quickly in your calculators. Tell me what you find. Okay, I simply quickly get a value there of 571. Okay, so that's 571.44 newtons. Okay, and it makes sense. Now think about it. The further away I go from the object, remember Newton's law stated that the force of attraction would be inversely proportional to the square of the distance apart. So it means that the further I move away from the object, the smaller that force becomes, isn't it? So the further this person moves away from the surface of the earth, the smaller that force becomes. So if you look at this force here in comparison with the one that that we calculated on the surface of the earth, you'll see that that force is now smaller than that force. Okay, right, so this is how we would tackle the question. Shall we grab another quick question? All right, so that we can make sure that we solidify the concept. And the last thing that I'm going to cover is just the graphs, so that you'll see what the graphs should actually look like. Okay, so the next question says, a 20 kilogram satellite is in orbit at an unknown distance above the Earth's surface. Right? If the satellite experiences a gravitational force of 164,000 newtons, okay, calculate the distance above the Earth's surface where the satellite is in orbit from. Okay, so if you think about it, so suppose here the Earth, here is the Earth, and here we've got a, here we've got a satellite that is in orbit. Of course, it's transmitting some electromagnetic waves there, and obviously it would be in orbit around the earth. So what we want to find out in this case, remember that the earth is pulling this satellite towards itself. There's a force of attraction that exists. Okay, and once again, we cannot use the formula for weight in this case. And why is that? Because remember, it's not on the surface of the earth, right? So in this case, we are now compelled to go and use Newton's law of gravitational attraction. Okay, right, so now what we're simply going to do is, okay, let's say, so the force between the satellite is going to be G. That's the mass of the earth, remember, multiplied by the mass of the satellite, okay, divided by the distance from their centers. So from the center of the satellite to the center of the earth. So that's the distance that we're looking for. Let's call that distance there d, and so this will be divided by d squared. So all we need to do is now substitute for all the relevant stuff. So they told us that the gravitational force is 164,000. So I know this will be 16400, okay? Or you can say 164 kilonewtons of force. And in this case, let's substitute all that we know. We already know, we said that G, that's 6.67 times 10 minus 11. The mass of the earth, we already said, that's 5.98 times 10 to the power 24. Okay. The mass of the satellite, they gave us that as 20,000. Okay. And in this case, we want to find out the distance d squared. Okay. Right. Now, let's try to find out what that distance is, okay? So what we simply are going to do is we are just going to cross multiply, okay? So let's do that quickly. Okay, let's try to make it easier for ourselves. We said we cross multiply So I've got 164,000. Okay, if you don't mind, I'm just going to write d squared over there, which is equal to, when you take that, put it in the calculator. So all I've done is take that 164,000 times d squared. I got that. 1 multiplied by all of that, I get 7.977. You know, I'm being really pedantic now. I didn't need to write all of this down, by the way, times 10 to the power 18, but I know some of you tend to struggle when it comes to these kind of calculations, but yeah, so it's also my duty to kind of assist. Okay, so we're going to divide both sides by 164,000. Okay, so that this cancels with that. We're going to divide by 164,000. What we do on the left, we do on the right, 164,000. Okay, and obviously upon finding we're going to take the square root. Remember, this is d squared, right? So whatever answer we obtain on this side, we take the square root of it. Okay, and what do we have as our final? Okay, I get an answer of 697,000. Okay, so what I'll try to do is just convert that into the scientific format. Okay, so let's say mode. Okay, there's scientific at 7, and let's make it to 2 decimal places. Okay, in fact, let's make it 3. So I get 6.97. Okay, please don't worry too much about that. So I just converted that answer into scientific form, right? So I get an answer of 6.97 times 10 to the power 6. And in this case, remember, that is in meters. Now, I want you to please remember, ladies and gents, what is that answer there? We've just obtained an answer, the distance between the center of the satellite as well as the center of the Earth. But what they asked me for was the distance above the Earth's surface. Okay, so in actual fact, what they are looking for is the distance from here till the center of the satellite, so above the Earth's surface. So in this case, what am I supposed to do? Okay, let's call that distance there, let's call it small r. Okay, all right, or in fact, you could have called this one here the entire distance r, and then we call that distance small d, whatever the case may be. Okay, so I've now decided to call this small distance there from the surface of the Earth to the center of the spaceship. I've called it small r. So now I'm going to try and find that that distance r there. So r would be, now think about it, so this entire distance, I found it to be 6.97, but remember, I also know the radius of the Earth, isn't it? So to find that distance, I'll say the total distance minus the radius of the Earth, and it should give me that small distance r, that small r there. So it should be, in fact, let's put it like that. Let's say r should be equals to d, which is the entire distance, minus re, which is the radius of the Earth. I'm sure you can pull that off quite easily. We already know what the radius of the Earth is, right? Okay, and I get an answer of 5.94 times 10 to the power 5. And remember, this is in meters. Okay, so that will be the distance away from the surface of the Earth. Okay, for those of you who are maybe worried about this answer, if you want to round it off, if you don't want to round it off, probably you should end up with an answer of 594,395.68 if you really wanted to be that pedantic about it. Okay, this is the answer that you would obtain. So we rounded it off to scientific format. we converted it to scientific form, and it was 2 times 10 to the power 5 in this particular case. Right, I hope that that's quite understandable. All right, so the last discussion that I want us to have quickly, ladies and gents, is to just simply talk about the graphs that have to do with this particular section. Okay, now very quickly, we said that if you look at if we were to draw a graph of the force against the mass, okay, the masses, so this, because they are directly proportional to each other, you remember that we said the force is directly proportional to the product of the masses. All right, so I'm expecting that when I draw this, it should be a straight line graph. Remember, anytime that you draw two things that are proportional to each other against each other, then I should always obtain a straight line graph. Okay, right. And then secondly, what if I wanted to draw a graph, okay, of force against the distance? Okay, so in this case, either if I have r, or the graph of force against the distance, the square distance. In this case, the type of because it's inversely proportional to the square of the distance, what I would find there, I don't know if so probably most of you have done maths. So if I draw a graph of the inverse like this, okay, y is equal to something over x, this would be a hyperbola, right? So in this case, I would obtain a graph that looks somewhat something like this, and it does make sense. The greater the distance, right, the more the distance between the two objects, what happens to the force? The force decreases, right? The further and further they are apart, the smaller that force becomes. Okay, right. But I have seen also in previous years, okay, where they actually had a graph of force against the inverse of the distance squared. Now note, I can put it to you this way. I can say force is inversely proportional to the square of the distance, or I can say force is directly proportional to the inverse of the square distance. Okay, yeah, I know that sounds a little bit technical, but yeah, all I'm just simply saying is that it is directly proportional. So the more the inverse square increases, the more the force increases. So you would actually, in this particular case, end up with a straight line. Okay, so once again, you'd find a straight line like that. So just be on the lookout for that. Yeah, I don't know if I need to elaborate even more about the graphs, but just remember that this is what the graphs look like. Okay, didn't want it to be quite a lecture, but this is what you would actually obtain in terms of the graphs that have to do with this section. Okay, so I want to leave it there, ladies and gents, and thank you for the privilege of you lending an ear. Okay, and please don't forget to subscribe. Okay, I see many of you have been telling your friends about the channel. Continue doing so, and I appreciate it very much. If you liked this lesson, please don't forget to hit that thumbs up, and please don't also forget to hit that subscribe button if you haven't, and I'll see you guys next time. Sharp sharp.